Hi, this video is on ionic bonding in compounds. In a previous video, we looked at why atoms form ions, and now we're going to look at why they bond together. So let's take the example of sodium chloride. Now, sodium chloride is an ionic compound, and it's made up of positively charged sodium ions, known as cations, and we can write them as Na plus for short, and it's also made up of negatively charged chloride ions known as anions, which you can write as Cl minus. Now, as soon as these positively charged and negatively charged ions form, they start attracting each other, and we have strong electrostatic forces of attraction between the oppositely charged particles. And this will happen between many thousands and thousands of sodium and chloride ions, and they will all come together to form a close packed structure, and it will of thousands and thousands of sodium and chloride ions, and in a giant lattice. So all of the ions will be interconnected to each other, and we can represent the structure of ionic compounds in different ways. One way is like this, and this is known as the space filling model. So here, this model shows how close the ions are to each other and how strong, because of the strong electrostatic forces. So if you notice, the sodium ion is attracting at least 4 chloride ions, but this is a two-dimensional diagram, and in three-dimensional space we'll have chloride ions in front and behind as well. So this is one way of representing the structure of ionic compounds. Another way can be shown as well, and that is over here. So here we have the structure of ionic compounds represented in the ball and stick model. So the circles represent the ions and the lines represent the electrostatic forces of traction. Now, if you look at the sodium ion, the cation, it is attracting one chloride ion above, one below, one to its left, one to its right, one behind, and it also be attracting one in front, which I haven't drawn. So there will be strong electrostatic forces of attraction in all 6 directions, and this will form a giant lattice structure, interconnected sodium and chloride ions, and it will also be a crystalline structure, a solid crystalline, because of the level of organization. So if you notice, a chloride ion will also equally be attracting other sodium ions. So a chloride ion will also be bonding to 6 sodium ions. The structure of the ionic compounds gives rise to certain properties. So let's look at the properties of ionic compounds. The first property of ionic compounds is that they have high melting points and boiling points, and they are solid at room temperature. And the reason for this is that to melt the ionic compounds, you need to break up the lattice. So you need to overcome the strong electrostatic forces of attraction between the oppositely charged particles, and this requires a lot of energy. So that's why they have high melting points and boiling points. Another property is that they are unreactive, and they are stable. So the ions have full outer shell of electrons, so they're very stable and therefore unreactive. A third property is that they do not conduct electricity when they are solid. So they do not conduct electricity when they are solid. And the reason for this is that in order to conduct electricity, you need to have charged particles that can move. For example, in metals, the delocalized electrons are free to move and therefore carry charge. But in ionic compounds, you have the charged ions, which are charged particles, but they are in fixed positions and they are not free to move, so they cannot carry charged. But they do conduct electricity when they are liquid or when they are in aqueous solution. So aqueous solution means that they are dissolved in water. So now the ions are free to move because they're in the liquid state. They're mobile and therefore they can carry charge and conduct electricity. Now let's take a look at which elements will form ionic compounds. So looking at the periodic table, the elements are arranged in the periodic table in increasing atomic number. They're also arranged into groups and into periods. But there is also another level of organization, and that is that they can be fairly neatly split into metals and non-metals. So the metals are on the left-hand side of the periodic table, that's group 1, group 2, that middle rectangular block, all the way up to aluminium, germanium, tin, polonium, and the star-like structure that I'm drawing. Now, all the elements to the left of this are classed as metals, and that includes the bottom two rows as well. And to the right of this structure, they're classed as non-metals. So that's group 8, group 7. So most of the elements in the periodic table are metals. Now, the metals have similar properties, and one is that metals, like that is group 1 here, and group 2, and the middle block here known as the transition elements, well, they will lose electrons to form positively charged ions known as cations. And the nonmetals will gain electrons to have a full outer shell of electron and will form anions. So the metals react with nonmetals in ionic bonding. And the reason for this is that the metals will usually lose electrons to get a full outer energy level and to form the cations, and then they will transfer those electrons to the non-metal, which will gain electrons to form an anions. So there needs to be a transfer of electrons from the metal to the non-metal. So you need a metal reacting with a non-metal in ionic bonding. But some elements are more reactive than others. So let's take a look at the periodic table and find out which one. So alkali metals, the group 1, and alkaline earth metals, group 2, are more reactive and more readily form the cation than for example, the transition elements. So that's the reactivity across the whole periodic table. But the reactivity can change down groups as well. So we're going to look at how reactivity changes down group 1 and also look at group 7. So looking at group 1 elements, so group 1 elements are from lithium all the way to cesium. And we're going to look at the reactivity down the group. So the first thing is that the atomic size or the atomic radius increases as you go down the group. And to find out why, we need to look at the atomic number. So the atomic number for lithium is 3, the atomic number for sodium is 11, potassium is 19, rubidium is 37, and cesium is 55. So the number of electrons is increasing, and the number of energy levels is also increasing as you go down the group, and that's due to electron-electron repulsion. So that's why the atomic size is increasing. So remember, in ionic bonding, group 1 elements will lose one electron, that outer shell electron, to form a cation. So now we need to look at how easy it is for that outer shell electron to be lost. Now, the electrons, all the electrons, including the outer shell electron, are held by the attractive force of the positively charged nucleus. So the nucleus is attracting all the electrons, including the outer shell electron. So if you notice, the outer shell electron is going further away from the nucleus, so the ability of the nucleus to attract the outer shell electron is decreasing as you go down the group, because it's just getting further and further away because the atomic size is increasing. So there is also another effect, and this is known as the electron shielding effect. Well, the electron shielding effect increases as you go down the group, and I'll explain what that is. Well, if you look at lithium here, lithium has 2 electrons in its inner energy levels, and sodium has 10 electrons in its inner energy level. Potassium will have 18 electrons, and those electrons are shielding the pull of the nucleus. So can you see, rubidium will have 36 electrons shielding the electrostatic force of attraction of the nucleus, and cesium will have 54. So this reduces the pull of the nucleus for the outer shell electron, which means that the outer shell electron is less tightly held and therefore more easily lost, which means that the reactivity increases as you go down the group. That ion is much more easily formed. So group 1 elements, the reactivity increases as we go down the group. Now let's take a look at group 7 elements. Now, group 7 elements, we're going to look at the reactivity down the group again. And they are from fluorine all the way to iodine. Let's look at the atomic number: 9 for fluorine, 17 for chlorine, 35 for bromine, iodine 53, astatine 85. So again, the atomic size or the atomic radius increases as you go down the group, and that I've explained that for group 1, so it's all the same for all the groups in the periodic table. Now we need to look at how easy it is to attract an electron passing by to that outer energy level. So that's the nucleus is going to attract it. Now the number of energy levels is going to increase as you go down the group. So that means you'll have a greater electron shielding effect. So there'll be 9 electrons shielding the pull of the nucleus for fluorine, but there'll be 53 electrons shielding the pull of the nucleus for iodine. So it's much more harder to attract, for the nucleus to attract an electron as you go down the group. So that's because the electron shielding effect is increasing as you go down the group, and because of that the pull of the nucleus decreases as you go down the group, so that electron is not easily gained. So gaining the electron, outer shell electron, and forming that anion reduces as you go down the group. So the reactivity decreases. So for group 7, the reactivity decreases as you go down it. So that's the trend in reactivity down group 7 and 1.